Let's begin by returning to our discussion of current sources and current sinks, specifically through the use of current mirrors. So last time I drew this little circuit for you guys. And as we saw before, these transistors are connected so they share the same gate source voltage, the same VGS. So given this, as we saw last time, we could show that if these transistors are identical in every way, including the same length, then it can be shown that I0 is equal to W2 over W1 times ID1, where this is ID1, the current flowing through the drain for M1. It gets mirrored over to M2. The difference is we can create a ratio between this current and ID1 depending upon the widths of the devices. And again, this is assuming L1 is equal to L2, which is pretty typical. That's actually quite common in modern circuit design. You want to make devices with the same length, but you can vary the width. Okay? And in fact, I want to kind of mention this. How do we normally do the width, multiples of width in IC design? You don't do it like this. Let's say you want a width of 2 to 1. You don't do it like this. You don't have one transistor and then one transistor that's twice as wide as the other. Turns out those are not as well matched as people would like, even though in every other way they look identical. But if you make one longer than the other, that really doesn't work. There's a better way people normally do to do things like this. They'll do this. If they want a width of 2 to 1, they'll create two identical transistors so that all three of these look exactly like each other. And then they'll connect these transistors in parallel with each other. And so this is what gives you your width to length ratio. And people call this is a fingered layout. It's like fingers on your hand. So this is typically how you will do these types of ratios, is by just creating identical matched devices and then connecting different transistors in parallel to get the different ratios you want. And so by being clever about this, you can create basically any ratio you want between two transistors. And in fact, quite often what people will do is, you notice these two diffusions here? They'll just move those together like this. So for example, that'll be the drain. These will be the source diffusions, and so they'll connect the source together, they'll connect the gates together. And so since they just basically merge the diffusions together to create a common drain. So this is very kind of common layout stuff. And although this is not a layout class, I wanted you guys to kind of understand how engineers think when they're doing the layouts for these types of circuits. All right? Now, we also talked about the performance of this circuit. What is the output resistance of this circuit? This thing is behaving like a current source, or in this case actually a current sink, if you want to be more formal about it. But what is the output resistance seen looking down into M2, given the fact we know it's going to be sinking some kind of current from some sort of load, some amplifier or some other circuit? Well, let's think about this for a moment. If I take this circuit and I convert this to its small signal equivalent, I'll get the following. since of course this is a circuit that has some dependent sources in it, I want to use source driving to find out what R sub O is. And this is GM times VGS2 same node. And the source is grounded, the gate is grounded. Let's just look at this part of the circuit here. There's nothing there but resistors and a dependent source. What are the voltages and currents in that circuit by inspection in that piece of the circuit? 0, right? Learned about that in circuits 1. If you build a circuit and there are no independent sources in it, just dependent sources and resistors, you can write the equations and solve if you want to. But by inspection, you're going to find that everything is equal to 0. So in this case, there's no way for this 1 amp of current to get over to that side of the circuit. So this independent source can't affect this part of the circuit. Nothing's connected to it. So in this case, I know all the voltages and currents are equal to 0. VGS1 is equal to 0. These are all equal to 0, all the voltages and currents in those resistors, which means that this is equal to 0. That's equal to 0 as well. Therefore, this is equal to 0 for that dependent source. So I could go ahead and do source driving, but what is R0 by inspection? Just RO2. What is RO2? Well, it's a large resistance, right? Typically in the tens or hundreds of kiloohms or megaohms. Now keep in mind, we want this transistor to behave like a current source. Does the fact that R sub 0 is large fit in with that? Yes, it does, right? Current sources have infinite resistance. Well, that's not infinite, but it's large. It's a large resistance. So we've been drawing these things before. We've been analyzing them. And you can easily see from small signal analysis, we do have large resistances. Okay? We've seen this before. We've done similar calculations with other circuits. Okay. Now, you can take this idea and you can improve upon it. Because a lot of people, when they design circuits like this, they would like that M2 to behave even more like an ideal current source. In other words, to increase the resistance even more. How do you do that? Well, we do it through a way we've already talked about. Let's look at an improved current mirror. If I wanted to increase R sub O, what technique did we talk about last time that makes output resistance larger? Cascoding, yeah. Why don't we cascode the current mirror? So I've cascoded the current mirror. I've taken the M1 and the M2, and I've now added these two devices to create a cascode effect. All right? Now, the current is still set by the ratio between M1 and M2. You can easily prove that to yourself. So what effect do M3 and M4 have? Well, M3 and M4, M3 creates the bias voltage for that cascode device. And what does this cascode M4 device do? Well, if we were to now go and calculate R sub O, I'm not going to bother to do the small signal diagram, but anybody want to kind of venture a guess at what the output resistance would now be if I were to actually look at it? Well, look at your cascode analysis we did last time. R sub O will be effectively equal to R02, the resistance seen looking down into M2, multiplied times the gain, the intrinsic gain of the M4 transistor. So now I've got a much improved current source that has now a much, much larger output resistance. It's more ideal. It more closely resembles an ideal current source. But of course, the assumption here you have to keep in mind is all these transistors have to be saturated. So again, we can now see how we can take a lot of these clever little ideas and start combining them together. It should be GM4. There we go. So we can see how we can combine these concepts together into the same circuit. And you know, we can actually do some other interesting things. Once you create a current mirror, you're not confined to mirroring the current just once. Because keep in mind, VGS is just a voltage. We can take this idea even further. Let's start with that original circuit up there, the M1 circuit. And I'm going to create a reference current. And let's say I now want to go and create multiple currents off of that same single reference string. That's easily done. What if I take 3 additional transistors and then connect them to that same gate source voltage? Each of them sinking a separate current somewhere in the circuit. And let's say in this case, the width to length ratio is equal to 1 for this transistor. The width to length ratio is equal to 2. The width to length ratio is equal to 3. The width to length ratio is equal to 1.5. And so in this case, let's assume we adjust R such that Iref is equal to 100 microamps. So this is what you do as a designer. You set that reference current by selecting the value of the resistor that gives you that particular reference current. And if that's the case, what currents do I now get for I01, I02, and I03? I'll get 200 microamps. I'll get 300 microamps. I'll get 150 microamps for those 3 currents. And in fact, I can keep adding as many transistors as I want. This is smart design because if you need to generate a current or multiple currents in a circuit, why do you need multiple reference circuits? One will do. Then you just go through and mirror whatever current you need throughout the rest of the circuit. Good, optimal, component-saving design. Now, of course, these are just current sinks, but keep in mind, anything I can do with an NFET, I can do with a PFET. What if I need to source instead of sink a current? Let's take a PFET, diode connect it, and let's flip that topology upside down. So now what I've got here is I have flipped the current mirror upside down, and now I'm sourcing current instead of sinking current. So now in each of these cases, I'm going to source the current into some other transistor or some other element. So, people will distinguish between this and the previous circuit. They'll say this is a current source, the other is a current sink, but really they're both, from an ideal point of view, acting like what we think of as a current source. So I'm not a stickler on the language, but you'll see that in books. They'll try to distinguish between a sink versus a source. But it's all the same idea. Okay, so you say, hey, this is great. I can now sink currents or source currents using current mirrors. All I need is 2 reference strings. Or do you? Do you need 2 reference strings? What if we do this? Let's start with a simple current mirror. And let's say with this simple current mirror, I set my reference string such that this current is equal to 100 microamps. Well, if I've got a single current device mirrored off of it with the same width to length ratio, then this is also going to be 100 microamps. So in this case, I'm sinking. But let's do this. Let's go over here and let's add another device and watch what I do here. This device is now connected to a diode-connected PFET. And so in this case, width to length ratio here is equal to 1, which means that I've got 100 microamps and 100 microamps flowing through both those devices. Except now the difference is the current in here is set by that device instead of by a resistor. And now I can go over here. Let's say I'm going to set the width to length ratio here equal to 1 and this equal to 3. And therefore, this will be equal to 300 microamps. And of course, I can continue this process on either the PFET or the NFET side. So I could take this, I could extend this with a width to length ratio of 2, and then this will be equal to 200 microamps and sink here. And up here, I can extend this with a width to length ratio of 2 and get 200 microamps here. And so I can sink and source currents in any ratios I want on both the top and the bottom side and extend this idea as far as I want, all of it running off of a single reference string. This is the kind of biasing you'll see in modern circuits. You'll build one good bias circuit to establish the reference, and then you'll mirror that bias through all the other transistors you need. So you can have one good bias circuit that literally controls an entire chip if you need to. So this is good. That's why you put all your effort into designing this, make it as good as possible. And this is a very simple reference circuit, but you can make more complex ones. But you put all your references, put all your effort into this, and then you can go through and take as many transistors as you want to extend this idea. Okay? This is incredibly common. Okay? You'll see this everywhere. Incidentally, what's the current flowing through these wires here? 0, yeah. You're just connecting into gates, right? So that the gates, there's no DC current at all. So that makes it very easy to extend this idea. All you're doing is you're just transporting a voltage, no current, across the chip. Okay? Now, just to quickly mention, you can do these same kinds of ideas with BJTs. The difference with the BJT current mirror is you have to deal with base current. So in this case, I've got Q1 and Q2. And I0 is going to be mirrored from IC1. But the problem is IC1 is not equal to IR. And why not? Well, because in this case, I've got IB2 and IB1 flowing into the bases, and they're being pulled off right here. IB1 plus IB2. And so IR minus IB1 and IB2 becomes equal to IC1. And so in this case, you can prove to yourself, I0 here is just IC2. So if you go through and you write the equations relating IC2, what you'll find is this. We can show this. So IC0, or pardon me, I0, which is equal to IC2, is just equal to IR divided by 1 plus 2 divided by beta. Because, of course, we know that in this case, IB1 and IB2 are just equal to IC1 divided by beta plus IC2 divided by beta. So if you actually write the equations like that and solve, this is what you get. So we have an error that's introduced by the fact that we have base current, a finite beta. If beta goes to infinity, IC2 just becomes like IR. It's like a MOSFET if beta goes to infinity. But otherwise, you'll have a mismatch because of beta. Okay? Now, this circuit works just fine. I mean, it works perfectly well if you're willing to tolerate the mismatch. But sometimes you can have circuits where the beta is kind of low, and you have quite a bit of mismatch between Q1 and Q2. So long ago, people came up with a way to solve that problem. How do you do it? Add another transistor. Here's my improved current mirror where in this case, I've still got my Q1 and my Q2, except I've inserted a Q3 between the collector and the base of Q1. And what's the idea behind this? Well, in this case, I've got IB2 here. I've got IB1 here. And in this case, the emitter current of Q3 then becomes IB1 plus IB2. What's the relationship between this current and IB3? Well, in this case, IB3 is equal to IB1 plus IB2 divided by beta plus 1. So now I had here IB1 plus IB2. Now I've got IB1 plus IB2 divided by beta plus 1. So that current's been dramatically reduced that's being pulled off of that node by the presence of that Q3 transistor. And so in this case, we can show that in this case, IC2 will be approximately equal to IR over 1 plus 2 over beta squared. So a dramatic improvement. So I can tolerate much lower betas in this circuit and still get a good match between IC2 versus IC1. So conceptually, you can see lots of neat little tricks. And these tricks, incidentally, I'm showing you, this stuff's been around for decades. People have been using this for longer than you guys have been alive, okay? So these are very old, tried and true, but they work very well, and no one's going to stop using them. But obviously, if you get into modern IC design, you're going to see these kinds of techniques. Okay? Now, just to quickly mention, in this case, I'm assuming Q1 and Q2 are identical. Yes?
So do you need like 3 transistors to make that one compared to like 2 transistors for the MOSFET one? And like, why would you want to use this one over like the MOSFET one?
Well, it depends upon the devices you have available to you. Do you have, for example, a bipolar process you need to design this in? Okay. In other words, you're right. If I were going to do this between a BJT versus a MOSFET, I would just use the MOSFETs. But I'm showing you this because in some cases you may be dealing with an older bipolar process, which you have PNPs and NPNs but no MOSFETs in it. Okay, so in this case you want to understand how this technique works. But your point's well taken. The MOSFET technique is infinitely more common in modern design. But just for completeness, I wanted to show you guys this as well. Okay, and incidentally, I should also add this. Here I assume that Q1 and Q2 are identical devices. There's no such thing as width or length in BJTs. So can I get multiples of a current? Yeah, sure I can. What if I wanted to approximately double the current compared to the reference current? How would I do that? What if I did this? Let's take a Q4. Let's just connect them together, right? Now each of these, Q2 and Q4, is now, in effect, mirroring IC1. So now in this case, what I've got is I0, which is approximately equal to 2 times IC1, just by connecting those together. And I can add 3 or 4. So this is like the fingering idea I showed you with the fingered layouts for MOSFETs. And only in this case, I'm not really fingering them, I'm just using identical bipolar transistors and just connecting them together in parallel. And so I get the same kind of effect. And I can add as many transistors as I want and get this current in larger multiples if I want to. So the same kind of idea at work. So again, I just want to emphasize that these techniques here, they rely on matching. So you can't go into the lab, for example, and pull a bunch of 2222s out of the drawer and connect them together and expect this to work. Not unless you very precisely match them together. So on an integrated circuit, however, they work beautifully because you can manufacture the devices right next to each other on the layout, and you know they're going to have the same characteristics. All right? All right. So questions about any of this? Okay. Well, yes, huh?
Why is the current for the second one approximately 2 times the original?
Because in this case, I'm assuming this current is approximately I0, and this current is approximately I0. Because I'm assuming, just as I did before, that, pardon me, I should have said here, actually this should not be IB2, this should be IB3 from that previous drawing, my apologies. So IB3 is IB1 plus IB2 divided by beta plus 1. Just make a quick correction. But no, getting back to your question, okay? In this case, we already said before, IC2 would be approximately equal to IC1 times, what was the equation there? It was 1 over 2 beta squared. So in this case, for IC2, this is approximately equal to IC0. Oops, hold on one moment. Okay, so IC2 is approximately equal to IR over 1 plus 2 beta squared, which if beta is large, is approximately equal to IR, which is approximately equal to IC1. So that's what I'm doing. I'm mirroring. This collector current and that collector current are very, very closely matched. So I'm just adding an additional transistor. So in this case, if this is equal to IR, then this one is also equal to IR. Again, assuming large beta. So in this case, this is equal to 2 times IC1 or equal to 2 times IR if I simply connect those collectors together. I'm just connecting them in parallel.
Wouldn't the base current be different?
No, the base currents are going to create an error. That's that 2 over beta squared. So the error is still there, okay? But I'm assuming it's small. But then once I connect these in parallel, I'm adding together the collector currents. So actually, if you go through, and hang on a moment here. If I were to go through and say, for example, I have M identical transistors. Let's assume I'm adding additional transistors. So for M identical transistors, we can show the following. I0 will be equal to M times IC1, which will be equal to M times IR divided by 1 plus M plus 1 over beta times beta plus 1. That's actually the exact equation you would get if you were actually go through and solve for the DC equations. So this assumes M transistors, however many you want to connect. So if M equal 2, then I0 would be equal to 2 times IR divided by 1 plus 3 over beta squared plus beta, which would be approximately equal to 2IR, assuming beta is large, okay, assuming beta is big. And of course, I could add as many transistors in parallel if I wanted to. I could add a third transistor in parallel. And then I'd have 3 times the current, or add 4 or 5, however many in parallel I wanted to do. So this idea of paralleling currents by or adding currents or increasing currents by paralleling devices, connecting them in parallel, extremely common. Okay? Yeah?
The current that is entering the collectors of heat energy, shouldn't it be approximately IC1 is the
Yes. Each of these is IC1, approximately IC1.
I sub
No, I'm sorry. I'm sorry. You're saying. Yeah, that was the original isobo. My apologies. You're correct. I should write this more correctly, shouldn't I? So actually, this should be equal to approximately IC1. My apologies. I was thinking of I sub O from the first circuit. Okay. So this is therefore IC1, approximately IC1 for each of these, which of course is equal to approximately IR for large beta. There we go. And their I sub 0 is then equal to that value there. So yes, thank you very much. Bad nomenclature on my part. Okay? So, again, current mirroring, extremely common technique. You see it everywhere. And you will see this idea of connecting these devices in parallel to some currents together. Extremely popular concept, very, very commonly used in IC design. Okay, so let's now talk about some other concepts that people use. We've looked at cascode amplifiers. We looked at basic current or basic gain cells. We've looked at current sources, current sinks, current mirrors. Now let's talk about cascaded, not cascode, but cascaded amplifiers. So in this case, cascaded with an A. What do I mean by that? I mean connecting amplifiers together, more than one amplifier. Let's say I've got 3 amplifiers, A1, A2, and A3. And we've looked at these different amplifier topologies. What I'm doing here is I am connecting the output of one amplifier into the input of the next and creating a chain of amplifiers. So in this case, here's my VS. And so in this case, these 3 amplifiers are chained together. What is the gain of this system? Well, in this case, this is VS. So for A1, the gain is V01 over VS. For A2, the gain is V02 over VO1. For this amplifier, the gain is V0 over VO1. So V0 over Vs, output to input, I can just decompose that. So I can just go and decompose that using the chain rule and break this up into the individual gains. So the overall system gain is the product of the individual amplifier gains. Now, when I build this amplifier, let's consider also the input and output resistance of this amplifier. What's the input resistance of this amplifier going to be? Well, clearly, it's going to be the input resistance of A1. What's the output resistance going to be? It's the output resistance of A3. So what do I get out of doing this? Connecting these amplifiers together, cascading them together. Well, one thing, obviously, I get a much higher gain. I can get a larger gain if I need it. But the other thing, let me just write that down. So for my advantages, much higher gain than a single stage. So I get much higher gain, but the other thing I get is this. I can mix and match my input and output resistances depending upon the types of amplifiers I use. So I can get different input-output resistance combinations than I could with a single stage. So I can have R in, R out combinations that a single amplifier stage could not provide. For example, let's say I require a low input resistance, a low output resistance, but a large overall gain. Is there any single stage amplifier that gives me both low input and output resistance? No. But what if I did this? What if I needed a low input resistance and a low output resistance out of a chain of 3 amplifiers? What would be a good choice for that first amplifier? Think about it from the MOS point of view. Okay? What would give us a low input resistance? What single stage MOSFET amplifier has a low input resistance, relatively speaking? Common gate, yeah. Common gate has a low input resistance. High gain, but low input resistance. We want low output resistance. What amplifier stage has low output resistance? Relatively speaking. I'll give you a hint. It has a gain less than 1. Okay? Yeah, common drain, right? The source follower. Common drain has a low output resistance. But then I want high overall gain. So what can I choose for that interior stage? What would be a possible amplifier I could use for that interior stage? A common gate or common source, right? Let's do a common source. Because a common source has a high input resistance, it's not going to load that stage. And so in this case, the first 2 stages give me plenty of gain. Gives me twice the gain I could get out of either a common gate or a common source amplifier. And then this common drain amplifier, I don't get any real voltage gain out of it, but I get a nice low output resistance. So by choosing my stages appropriately, I can mix and match the properties of my amplifier. Neat, huh? So it all comes down to understanding how the basic single stage amplifiers work and then connecting them together. All right? Now, once again, when we're looking at this kind of situation with cascaded amplifiers, I can do these in one of two ways. I can capacitively couple them. So I can capacitively couple these and put a large capacitor between these to connect those stages together. And what's the advantage of this? Well, we already know that. The capacitors enable us to separate the DC biasing from the AC performance. But what's the problem with using capacitors in circuit design? Expensive. They're very, very pricey. So instead, what do we do with these types of circuits? We DC couple them. We just connect them straight together, output to input, just the way I drew it up there. So in this case, the biasing, the DC biasing, can now interact between the different stages. Okay? So but what's the advantage of connecting them together? It's cheaper, no capacitors. So DC coupled, and we've already talked about this, DC coupled is the way to go in IC design. All right, so having said that, let's look at some very simple configurations where we can couple two stages together. But when you look at them, they're not so obvious as you might think, because when people try to cascade amplifier stages together, quite often they try to sort of merge the topologies together. Let me show you some examples. Here's some examples of some two-stage cascaded amplifiers. Here is a common drain, common gate amplifier. So in this case, I've got first a common drain stage. Here's my input. I'm taking my output at the source of the first transistor, and then I just do this. I have a current source load. Notice this is equal to 2I. So therefore, this current must be equal to I as well. So I plus I is equal to 2I. And the output of this amplifier, I'll call this Vs the source voltage, then feeds directly into the source of this amplifier. And then here's our output, Vo. So this is our common drain. This is our common gate. And notice they're sharing the same component. They're sharing the same current source. So people try to make these more compact. If you can take two components and merge them into a single component, that's good design. We see that exactly here. So in this case, I've got both a high input resistance and a high output resistance. What type of gain do I get out of this? I get a large non-inverting gain. This is a gain of about 1 from Vs to Vn, but then I get a high gain here. So now let me draw a totally different looking circuit that does the same thing. So in this case, here to here, Vn to Vs, is once again a common drain amplifier. What's the load? It's not a resistor, it's not a current source, it's the other transistor. That's the load that's connected to this common drain amplifier. So here's a common drain with an INFET, and then down here I've got a PFET. It's creating inputs going into the source. I've got V bias here. I take the output at the drain. So I get a common gate. In this case, it's a PFET. So a common drain INFET and a common gate PFET. Same circuit as that in terms of functionality. The difference is I used another INFET, or rather a PFET transistor in place of a second INFET transistor. So you can kind of see how these little clever little topologies work. And when you sit here and look at these multi-amplifier topologies, quite often you have to kind of look at each transistor and think, what's that acting like? Is it acting like a common emitter, or is it acting like a common base, or a common collector, or a common source, or a common gate, or a common drain? And you have to kind of trace the signal path. You say, oh, from here to here, oh, that transistor is acting like a common drain. That's a source. That's a source follower. Then from here to here, it's going into the source, coming out the drain. That's acting like a common gate. Except that it's a much more compact and elegant design. The way we're saving components. Pretty cool. All right. Here's a circuit that looks a little more familiar. Here's my input. So what do I have here? Common source amplifier. Common source, common drain. So what do I get out of this? I get a high input resistance, because in this case I'm looking into the gate of the first transistor. The output resistance, I'm looking up into the source of this transistor. And so I have a low output resistance. And once again, I get good gain from the common source stage. Okay, in this case, this is inverting gain, a high inverting gain. So you always want to think about this. When you go from a gate to a drain, you invert. If you go from a source to a drain, you do not invert. And so you can think about just how it flips, thinking about whether it's common gate versus common source, or rather, common gate versus common source. And so this is a common source, common drain amplifier. Now, you can do this kind of trick. This is more familiar to you guys. You can do this kind of trick with BJTs. So I can do the same kind of trick here with a BJT that I can with a MOSFET. But you know, this is a somewhat trickier design than this design. It's a little more difficult to do that design. Can anybody tell me why this design is trickier than that? Or rather, this is more difficult than this? Anybody want to venture a guess? Well, let's think about this. What's that input resistance? Theoretically, looking into that second stage. It's infinite, yeah. What is the current, DC current going into that second stage? 0. Is that true over here? No, it's not. Over here, this is not true. There is a base current that must flow into that second stage. This second stage needs base current that the first stage needs to supply. So in this case, IB of the second transistor affects the bias of the first transistor. So you can certainly do these things with BJTs as opposed to MOSFETs, but it's a trickier design because you have to account for the effects of the base currents and the fact that you don't have you may not necessarily have a very high resistance because of the fact that that base current is there. So you got to be careful. So this is actually a little more challenging to design with than MOSFETs, where you don't have to worry about gate currents. Okay? Questions about this? Now, there are a lot more circuits in the book showing these kinds of examples of circuits, cascading them. I'm not going to spend any time on them. You guys can look in the book yourselves. But there are lots of different topologies where we can combine together multiple transistors to essentially cascade these together. But any one of these, you actually have the tools to analyze these yourself. You can do the DC calculations and the small signal calculations on your own. You now have those tools. So that's the beauty of this. Once you understand how to analyze the single transistor stage, you can expand this. So any circuit you see, even if you don't know what it does, you can sit down and write out the equations and you can figure out what it does. And that's the beauty of this. Trying to memorize this stuff is hopeless. It'll never happen. You have to learn the technique, and then you can analyze anything that's thrown at you, including on the final exam. Anything I give you, I guarantee you, it's not going to be anything you've seen in the book or in the homework, but you'll be able to work it, I guarantee you, if you understand the technique. So questions about this? Okay. This leads to our last topic, which we're going to just talk about for a couple of minutes, but come back to next time. I made you guys a promise at the beginning of this semester. I told you that by the end of this semester, you would know how to design an op-amp. All right? Let's draw an op-amp. Okay, here's an op amp. How does an op amp behave? I've got a large open loop gain multiplied times the difference between the non-inverting and the inverting voltages. What kind of output resistance does an op amp have, ideally? Think back, 2112. Ideal op amp has what kind of output resistance? 0, yeah, because what does the output of an op amp behave like? It behaves like a dependent voltage source, right? We remember that. So this is low. What are the input currents of an op amp ideally? What are the input resistances? Infinite, absolutely. Good. Okay. What kind of output stage could I use for an op amp to get a low output resistance? Yeah, a common drain amplifier, right? Source follower. But here's the trick. How do I get something that is the difference between two voltages? All the amplifier stages we looked at so far had a single input and a single output. How do I get this? Well, this leads to our last amplifier topology we're going to look at this semester. And that is called the differential amplifier. Now, we've heard this word differential amplifier because we took an op amp circuit and we added resistors to it in 2112 and called that a differential amplifier or a difference amplifier. But here what I'm going to do is I'm going to show you guys how to build a differential amplifier using transistors. And we can kind of think of that as the fourth fundamental transistor stage, the differential amplifier. But it requires more than one transistor. It requires a minimum of 2 transistors to make it work. And it turns out, we're going to look at this next time, the differential amplifier has a really interesting property. Not only does it let us amplify the difference between 2 voltages, it also allows us to get rid of bypass capacitors in an IC design and create a small signal effective virtual ground, which is incredibly useful in IC design. So next time we will look at that final stage, the differential amplifier, and then we'll put everything together we talked about today with the differential amplifier, and we'll design an op amp. All right, and that'll wrap this class up. Okay, I'll see you guys on Thursday.